Welcome. This lesson is going to tie together Riemann sums and antiderivatives. So, antiderivatives, an observation of Newton and Leibniz, let a of x be the area under the curve y equals f of x between a and x. Then a prime of x equals f of x. Now, what does that mean? All right, well, we have a curve here, and we're finding the area under the curve. Right? If a of x is the area under the curve, then the curve that we're working with is the derivative. So in other words, to evaluate cumulative change of a function, we sum up the area under the derivative. So for instance, if we want to find the change in position, we sum up the areas under the velocity curve. Right? And this will have some, and we will go over this a little bit more, so it's just a little introduction. This particular lesson here will include some some notation, a little bit of new concepts, but mostly review. And then it's in this lesson, but the next podcast, we'll start with all new. So reviewing these symbols, right? So you saw at least some of these symbols when you did the antiderivative lesson. So what do all these symbols mean? So we have that elongated S. It is the integration symbol. When we have limits on our integrand, we are literally summing up areas. So that's why an S is used for summation. We have a lower limit of integration, that's our starting value, and we have an upper limit of integration, that's our ending value. Much like when we have the start and end to the Riemann sums. We have a specific interval for Riemann sums. We will have a specific interval for these definite integrals. We have to have a integrand, and that's the derivative. Right? So when we integrate, we're finding the area under the derivative. At least when we integrate, and we find what's the area under the derivative if it's a definite integral. If it's not a definite integral, then we're finding the function who has that derivative. But this one is these are all definite integrals. And then variable of integration, right? And it does have to be the same variable as the variable in the integrand. Let's compare that to a Riemann sum. So before we were working with Riemann sums, but we weren't dealing with the limit. So if we sum up the Riemann sum, so the f of xk there, those are all the rectangle heights. And we multiply that times the change in base, the change in x, right? And change in x is the difference in the end value and the starting value divided by the number of subintervals. Right? That we use that to approximate the area under the curve. Well, now we're doing the same thing. Right? If it's k equals 1, by the way, it's a right Riemann sum. For these ones, it won't matter as we get started with new material. It won't matter whether it's a right, a left, or a midpoint Riemann sum, but I find the right Riemann sum a little easier to work with. That just makes it easy to do the same thing, because it won't matter now, because with you're going to be getting the exact answer. So now we're not just summing up a finite number of rectangles. We're taking the limit as n approaches infinity. So that means we're going to have an infinite number of rectangles. So n equals an infinite number of rectangles when we want to find the exact area under the curve. And that corresponds with the integration. The summation symbol matches sigma. The limits of integration match the interval. We have our function. And then the variable of integration is our change in x. But don't forget, we are still finding the area under the curve. Now to evaluate the definite integral. We're going to go over a couple of things, and then we're going to look at a little bit of review before I start the new material. So the definite integral from a to b of f of x dx is a number. It does not depend on x. We could use any letter in place of x, so long as, without changing the value of the integral, so long as the variable of integration matched. Right, so the sum where here we have a Riemann sum. If there's no limit, we're just summing up a finite number of rectangles, then it's a Riemann sum. if we take the limit as n approaches infinity of that Riemann sum, we will have the exact area under the curve. And of course, Riemann sum is named for the German mathematician who developed and worked with Riemann sums. It got named after him. I don't think he called it after himself when he was working with them. And that's Bernard Riemann, born 1826, died 1866. I think it was named later in his honor for his work he did with area under the curve. He did not live a long time, so he certainly deserves to have something named after him. He's quite an influential mathematician. So we see the definite integral, f of x from a to b dx, can be interpreted as the area under the curve y equals f of x from a to b. So when we are finding the definite integral, which is the limit of the Riemann sums as n approaches infinity, we are actually finding that area under the curve. No more approximating. Although you still need to be able to approximate because we are a little limited here on what kind of functions we can find the exact area for. So the ones that we will be finding the area for are ones that we have a summation rule that we could use to rewrite it and calculate as n goes to infinity. Right? So we'll be dealing with constants. Right? So if we want to sum up n number of constants with k equals 1 as our first value, you just take what that constant is and it becomes a coefficient. So it's just c times n. So if I wanted 54s, for example, that would be 200. 50 times 4. 4 being what I'm adding up a bunch of 4s. How many of them? 50 of them. That would be 200. We have the sum of a finite number of n's, or k's here, k's, where we're starting with the first value, and we're going to have n k's. And we learned this in the summation rules lesson. The rule would be n times n plus 1 divided by 2, but we're going to be taking a limit, and n is going to be going to infinity, and that formula is just not going to be very friendly and would require us to do extra work. So it'd be better if we just simplified it right from the beginning, and then we don't have to keep doing the same work over and over again. So if you distributed the n and divided by 2, you'd have the expression next to it, n squared divided by 2 plus n over 2. So we'll use that as the summation formula if we're adding up n x's. If we're adding up n x squareds, right, we learned the formula, n times n plus 1 times 2n plus 1, all divided by 6. If you multiply those together and divided by 6, you'd have n cubed divided by 3 plus n squared divided by 2 plus n divided by 6. And finally, if we're summing up a number of x cubes, starting with the first value, we have a formula for that. N times n plus 1 divided by 2, all squared. If you distributed the n divided by 2 and squared, you'd end up with n to the 4th divided by 4 plus n cubed divided by 2 plus n squared. Right? And all of these are starting at the first value. That's why it says k equals 1. So we have these handy-dandy summation rules. So now you know why I taught you about summation rules. These are the only ones we will be using. Right? And it allows us to sum up a very large number of x's or constants very easily. And we're going to need that because we're going to be summing up an infinite number. So before we move on to some new material, let's review Riemann sums, right? Because that's what we'll be doing, but we're going to be taking a limit of Riemann sums. So it's going to look just a little bit different. But if we were approximating using Riemann sums, right, so let's look at our left Riemann sum. We have the change in x. Because we only want to have to multiply it one time, because it gets a little tedious to multiply it, in this case, 12 times, we will sum up all our rectangles first, and then multiply by the change in x. And we are starting with the first value. After that, we're adding in our change in x. Right? So the very first value would be f of 0. After that, it's f of 0 plus change in x. In this case, the change in x is 1/2. And we would plug that into our formula, our equation there, which is f of x equals x squared. I've already found all the y values, all the heights of the rectangles, because, well, I didn't want to see me have to sit there and write down and square numbers. That's kind of a little tedious. All right, but we'll do the summation part. So for the left-hand Riemann sum, we will use all, but the hard to see for me anyway, value at the bottom there, right? The left Riemann sum always uses the left value. It never uses the last value because that would be on the right-hand side. So for this would be L12, there are 12 subintervals, 12 rectangles here, and we're using left sums. We're going to take the change in x, which is just our ending value, 6, minus our starting value, 0, divided by the number of subintervals. So our change in x is 1/2. So we're going to multiply that 1 time times all the rectangles, and the values we use are the left-hand ones. So after you've gotten good at doing these, sometimes you can, like in a problem like this, I can leave the graph off and know that each one of these is a rectangle, and the value on the, I'm going to use every value, because every value here is going to be a left-hand side, except for the very last one. So 0 plus 1/4 plus 1 plus 9/4 plus 25/4 plus 9 plus 49/4 plus 16 plus 81/4 plus 25 plus 121/4. Now I'm just going to change a few of them. I'm going to leave them in terms of fourths. I can add a little bit easier that way than I can work with decimals. I have to use a calculator through the whole thing if I was using decimals. I'm going to change that 25 to 100/4 so I can add it with everybody else. This would be 64/4. This would be 4/4. Anybody else? 36/4. All right. Add that up real quick. And so I can just add the 1 plus 4 plus 9. All right, so that'd be 14 plus 25 plus 36. And we got a 49, 64. Actually, I could just take 145, add those two together. And then 221. So I'm just kind of chunking them together because some of them are kind of easy to add up. So I got 490. So L12 equals 1/2 times 490/4. I can divide 490 by 2 and reduce that. So that would be 2, and that would be 245. And so the left Riemann sum, come on, I recall writing some numbers in there. Maybe not. And I know I wrote them. There we go. 245. There we go. All right. So our left Riemann sum is going to be 245/4. This would be an underestimate. And that would be because f of x is increasing on 0, 6. Right, so it'll underestimate on an increasing function because the right-hand side is larger than the left-hand side. All right, so I don't know why there's an arrow there, but we'll get rid of it because I don't think I need it. All right, so now we have the right Riemann sum. The right Riemann sum does not start with the starting value. It starts with the very first value. All right, so j equals 1 is referring to the first rectangle. So we have, instead of starting at 0, we're going to start after the change in x. So we're going to start with 1/2. So here we're going to skip the 0, right, the f of 0, because that's on the left-hand side of a rectangle. All the other values are on the right-hand side. So the second value is the first value for the right-hand side, and the third value is the second value for the right-hand side. So just imagine little bars, right? And we're choosing the right-hand value. So the right-hand Riemann sum uses everything but the first number. All right, so let's write down. Still the same change in x, that won't change. So our right Riemann sum, we would have 1/2 times, we'll skip the 0, 1/4 plus 1 plus 9/4 plus 4. Why do I think I left off the 4? Did I leave off the 4? Hey, what happened to the 4? Yeah, there's no 4. He got left off. I just realized that on the left Riemann sum. Well, don't do that. So the 4 should have gone right here. I should have realized I had 2. I was writing quickly. Let's just switch those. So this was a 4, which would have made that 16/4. Well, it's a good thing I noticed. So this number's not going to be right, because we forgot little old 4. Probably because the 4 kind of blends in with the 4 in the denominators. So that was 490. So if I add another 16 in, that would be 506. And that was 4ths. We won't forget you again, little old 4. So I don't think 506 is divisible by 4. Let's find out. No, it is not. So we can divide by 2. So 253 and 2. And so that should be 253/4. Ignore the number we got the last time. All right, let's continue with the left Riemann sum. And this time we'll make sure we didn't forget anybody. 1/4, 1, 9/4, 4, 25/4. Let's make sure each time we have an integer and then a number with a 4 in the bottom. 9, 49/4, 16, 81/4. You know, another good way you could tell that you didn't forget anybody is to count. 121/4. So that's how you come up with good strategies so that you don't forget things, is you make a mistake and then you're like, oh, I should do something so I don't make that mistake again. Let's actually check. On the left Riemann sum, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12 values on the left. How about on the right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and we have 12 values on the right Riemann sum, so it's okay. And then let's change this to 4/4 and 16/4 and 36/4 and 64/4 and 100/4. Now notice they're all the same values again. We skipped the 0, but the 0 didn't do anything anyhow. Oh, the 36. And 36 would be 144/4. So the only thing that's different is we have that 36. So let's just do 1/2 times. Before we had 506. I'm going to assume that there were no other mistakes. I see 12 values and all the right 12 values. So 506 plus 144 is 650. Divided by 4, and we could reduce that. Make this 325 and make that a 2. So that would be any day now. Oh, I think as I picked up the blue pen, now it wants to make it in blue. 325 and 2. How about now? There we go. So that would be 325/4. And notice it is greater than the left Riemann sum. This is going to be actually an overestimate. I'll write in red so it stands out a little bit. Oh, and let me clarify on my comment there. I knew I was talking about the left Riemann sum, but if I just put some value was an underestimate because f of x is increasing, that's really not a complete answer. So let's make that the left RS Riemann sum is an underestimate. And the right Riemann sum is an overestimate because f of x is increasing on 0, 6. So it's a good idea to make that real clear. Yes, we wrote the underestimate next to the left Riemann sum and the overestimate next to the right Riemann sum, but we should make that really clear. For the midpoint Riemann sum, we would just use the halfway points in between the left and the right hand values. So instead of f of 0 being the first value, so f of 0 was the first value for the left Riemann sum. F of 1/2 was the first value for the right Riemann sum. Halfway in between that would be f of 1/4. So the midpoint Riemann sum uses f of 1/4, f of 3/4, f of 5/4, etc. So the midpoint uses the x values halfway between values for the left and right Riemann sums. Right? So it's the midpoint of the rectangle that is used. Now I'm not going to do the midpoint Riemann sum as well. We did a lot of midpoint Riemann sums, but I am going to do a trapezoid Riemann sum real quick. So evaluating using the trapezoid rule. So same values, right? But we're using trapezoids instead of rectangles. So you know for trapezoids, we take the two bases. So we take the left-hand side and the right-hand side and average them together. Now, because we're averaging two values, our change in x, instead of being 1/2, is going to be 1/4. So it's going to be this, but divided by 2n, so that will make this 1/4 for the trapezoid rule. I might as well get rid of the word left. That was for the left Riemann sum. Go away. There we go. All right, so trapezoid, not 16, just 12. 12 is enough. All right, so we're going to have 1/4. And then the first value is only used once because it's only on the left-hand side. Right? But the second value, the 1/4, is the right-hand side of the first bar, left-hand side of the second bar. So we have 2. 1/4 and 2 of every value. That's a 4. Hopefully you can read that. Of every value except for, not going to forget that 4, except for the first and last. 25/4, that 4 really does blend in, plus 2 times 9, plus 2 times 49/4, plus 2 times 16. And it's easy to leave, especially when you have this many, to leave a number off. So I like that idea I came with. Count. Make sure we got the right amount of values. Now we're not going to have 12 values for the trapezoid rule. We'll actually have 13, right? Because we used every value. All right, oops, and don't forget your 2 here. 2 times 25, and then 2 times 121/4, and then 36. There we go. There's all the values, and let's make sure we got 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Good. I'm feeling good about that. So let's simplify that. We still have our change in x. Get rid of the 0 at this point. I wouldn't, if you're writing a Riemann sum on an FRQ or on anything, write the 0 in. It shows you know that was one of the bars, all right? Otherwise, a reader, a grader might think you didn't know it, right? So you didn't know that that 0 counted. So the 0 counts. It is one of the bars, right? But it doesn't change the value at all. Now when we're simplifying, we can drop it. All right, so 2 times 1/4 is a half. And then we have plus 2, plus 9 halves, plus 8, plus 25 halves, plus 18, plus 49 halves, plus 32, plus 81 halves, plus 50, plus 121 halves, and then plus 36. All right, so if I want to combine, I guess we could just make it, 0.5, or I could change the integer values. I've been changing the integer values. Let's just change it. So this would be 4 halves, and this would be 16 halves. And this would be 36 halves. Although I see me writing, I don't see a lot of numbers popping up. 64 halves. There we go, all at once. 100 halves. And 72 halves. All right, so let's add those up. So we have 14, if I add up the first 3 numbers. And then 41, and 36, and 49, and 145 if I add up the 64 and the 81, and then 221. So I'm just kind of chunking the easy to add numbers together, and then the 72. Gives me 578 halves. So this would be 1/4. Come on. 578 halves. And yeah, I can divide, I can reduce, but just this part here. This part here would be 289. So 289 fourths. I'm going to write my answer in, and let's see how long it takes to come up. So 289 fourths should be in between the other numbers. It's 72. 72.25. All right, put my 4 there. Come on. I wrote a 4. I wrote a 4 twice already. That's my third 4. I'd like to change the page. Boy, it's being obstinate. It just doesn't want to make a 4. There we go. About time. Probably get like 4 of them now. All right, let's go to the other page. I don't remember what it was. And let's check out what that value was. So we had 253 fourths. Oh, actually, they're all divided by 4. We don't need to. So we had 253 fourths. That was an underestimate. 325 fourths. That was an overestimate. And let me just, so the 253 fourths was 72.25. The trapezoid rule, was 63.25. The trapezoid rule was 72.25, and if we take 325 and divide it by 4, we get 81.25. So you see the trapezoid rule was in between the other two, and it should be. Now, we've done some approximating. Now let's find the actual number. So it is not, I'm going to put the decimals here so you can see them. So the left Riemann sum here as a decimal so we can compare, was 73.25, or 63.25. The right Riemann sum, I'm just kind of put it up here, was 81.25. So the 63.25 was the underestimate. The 81.25 is the overestimate. And this one here was 72.25. Of course, they were all divided by 4, I realized afterwards. And we could have still compared them without reducing. But so you can see that one is in between. Now let's think concave up, concave down. What kind of function is this? Well, f of x equals x squared. This is concave up. So as a reminder, trapezoid rule overestimates if f of x is concave up. So this is an overestimate as well. So the exact value is in between the trapezoid rule and the left-hand Riemann sum. But let's find out exactly what it is in the next video. So I'm going to pause this video and I'll meet you in the next video.